Got this, which I don't need. Okay. All right. So we have the vector valued function e to the t I plus sine of t j plus ln of t k. Find the following values. So it's very similar to number 3, except it's not asking you to go through the limit definition, and it won't. That was the pledge I made last time, where it was, I'm going to ask you to do a limit definition problem on the test, but I'm not going to ask you to do it with anything crazy in terms of functions. Although it would be kind of fun to maybe tackle a problem one of these days together. Just not something I would put on a test. It's a little too much. Time-wise, it doesn't really serve the kind of purpose that you might think at first glance. Anyway, evaluating the function for pi over 4. So I'm just replacing all my t's with a pi over 4. Plus sine of pi over 4. So I'm going to go through and just kind of on the fly make my substitutions. And if it cleans up reasonably, this is one of the drawbacks with not using the Apple Pencil, that it doesn't do the palm rejection the way the Apple Pencil does. It gets confused whenever my hand touches the screen. So that's going to be a little aggravating, but it is what it is. So sine of pi over 4 is radical 2 over 2. And then the natural log of pi over 4 is something that we just got to live with. Or maybe we get to live with, depending on how you look at things. Right, and that's multiplied by the unit vector k. All right. Make a little bit better of a plus sign. All right. Now, this function, it's really asking, is it continuous? But it's sort of like, in order to answer A and B, you sort of have to have a sense of whether or not it's continuous going into the problem. But there's no reason to think that it wouldn't be, because the only function in this vector valued function that may not, or might break continuity, if you want, is the natural log, because e to the t and sine of t are everywhere continuous. The natural log of t is the only one that gets a little wonky. Right? So when we find the limit as t approaches pi over 4, there's no funny business going on around pi over 4. So it ends up giving you the same result, which is great news, because that means that this function is continuous at pi over 4. And again, that's because the answers for A and B are the same as one another. And they're the same and they exist. If they didn't exist, that would be a different story. Pi over 4, I don't know what that is precisely, but I know it's a value that is going to be satisfied in the domain of the natural log. It's going to be a positive number. Right? But if your curiosity gets the best of you, I honestly can't remember if it's in one of these. Yeah, there it is. I know we played around with this last time. I just couldn't remember. The natural log of pi over 4 is a negative number, but you could have a result of a natural log that's negative. You just can't take the natural log of a negative. So, if you were curious, that's what it would be. There's nothing wrong with that number. It's a real number. E to the pi over 4, if you want to see what that is. It's, I don't think I have an E. I think it just goes straight for E. Yeah, if I remember correctly, that's E. And we're raising it to the pi over 4 power. And you can see that's about 2.19-ish. But there's nothing wrong with leaving it in the exact form. And in fact, that's encouraged. So that's where we're at for that one. Now, just because I want to, what I'm going to do is I'll bring it over to the Geogebra. A weird thing to say. Just so you can get a look at it. I'll stop this share. and start this share. So I'll pop in this curve, right? Because really, in effect, we're looking at a parametric equation. You know, vector value functions are, modeled parametrically. So curve e to the t sine of t. I'm putting it in component form. Put it in parentheses. Natural log of t. Put that in parentheses too. Comma variable t, comma low bound, high bound. Now t should be restricted because the natural log function, again, you can't take the log of 0, you can't take the log of negative number. So I want to have values that are bigger than 0. But what I can do is I can just start it at 0 and just go from there. And so this is what the function would look like. It would truncate it so that you're not actually going to get to 0. It says t is greater than or equal to 0, but we know better than that. And if you want, you can, I suppose you could put like 0.0001 or whatever, but that doesn't really serve much of a purpose. All right, let me get rid of this. And then you can see here, we're looking at this sort of pathway. All right, it's got characteristics of an exponential function, definitely, a logarithmic function. It seems to have that leveling off component. And zoom out here. Definitely very much more exponential logarithmic than what we would see in terms of the sine function, the trigonometric component, right? Now, you do kind of lose a little bit with GeoGebra. It gives you a good idea of what's going on, but the problem is you try to zoom in too much, and it kind of lets you down. So, you know, is this a smooth curve? Probably not. That sine function is probably going to have some sort of impact on the y value and how it manifests itself. But, you know, we can't really get too close in without it just kind of freezing up on us. So, you know, you got to figure that the sine function is going to play some kind of role in there, but it wouldn't be until you investigate it further that you can see what kind of role that is. But it's just, I figured it's a good opportunity to refresh your memories on how you plot a parametric, because that goes along, you know, hand in hand with the Bezier curves and things like that with the tech assignment. So just something to look into. So we're going to hop on over to page 44. So let me stop this share, stopping that share, starting this share. Oh, good times. Let the good times roll. I entertain myself. Okay, these are our rules again. So what I'll do, just so I have something to point at, because it's really just essentially our, you know, the rules that we're familiar with, but nothing wrong with having them on the next page also. So I think maybe I'll take that as a typo. I mean, I'll definitely take it as a typo. I don't know if it's necessarily anything that I'll do anything about, but it might make more sense to have these rules on the same page as the examples that they correspond with. But, you know, I'm just going to kind of chuck them in there. Yeah, it might even, that actually isn't even a bad look. So that would work. Okay, so let me get rid of this stuff. So we're looking at calculating the derivatives using the properties, but specifically we're talking about the dot product, right? So the rule that involves a dot product, talking derivative of the first function dotted against the second function vector value plus the first function dotted against the derivative of the second function. So, you know, here it's, you know, in our rules, it's R and S, but we're looking at a model that talks in terms of R's and U's. So we'll make that adjustment. Right. So this is going to be R prime of T dotted against U of T plus U prime of T dotted against R of T. right? So that's just our setup. I do need to know the individual derivatives. Some are easier than others. None of them are difficult because they're all related to polynomials, and we do them a piece at a time. So r prime of t is going to be equal to, let me clean that up, 6i plus, this would be a binomial 8t plus 2 j plus, or quality plus 5k. All right, so that part's not too bad. The components that make up the vector, the derivative vector, you can look at separately, and in fact, we'll look at them in component form in a second. But for now, we'll just get the derivatives down on paper. So u prime of t, 2t I plus 2j, and another binomial, so plus 3t, I got that backwards, geez. 3t squared minus 3k. All right, that hopped away on me. All right, so water. So I got a dot one against the other, against the other, and against the other. Add it all up, see where it takes us. What I'm going to do is I'm going to just kind of rewrite all this stuff here in terms of component vectors. So r prime, 6, 8t plus 2, 5, dotted against u in its original form. That's where it gets a little dicey, the fact that the original vectors are not too neighborly looking. So t squared minus 3, comma, 2t plus 4, plus, comma, t cubed minus 3t, for quality exponent. All right, so that's the first bit. Then we got to add to that u prime dotted against the original r. All right, so I'm just going to do that in a second line here. So my u prime is going to be 2t, 2, and 3t squared minus 3. That's getting dotted against 6t plus 8, that trinomial 4t squared plus 2t minus 3, and then 5t. So that's what we have to expand and evaluate. Not the nicest thing in the world, but somewhat manageable. Because right? Again, it's just polynomials. Doesn't mean you're going to have fun doing it. It just means it is doable. It's mindless, tedious, whatever, but it's not mentally rigorous. All right. So let's kind of move it on down the line here. I'll use my highlighter strategically here. So this going against this. These, oops. That's part of the fun. So we're looking at 6. Oh, also, since it's dot product, our result is going to be a scalar, so I don't need my vector notation here. All right, because it's going to be the products added together. It's going to be all big polynomial. If we're lucky, it might clean up nicely. We'll see. All right, so 6t squared minus 18 plus, so I'm distributing this against this now. That's going to be 16t squared plus 32t plus 4t is going to be 36t plus 8. And then the final components, 5 times t cubed minus 3t is going to give me plus 5t cubed minus 15t. All right, so I got that part. Next part, it's going to be a little bit different, but I don't think it's going to be too crazy. We kind of lucked out with the middle term in the first vector because that ended up being just a monomial. If it was more complicated than that, then we would have kind of a fun time distributing that against the trinomial in the middle, but we kind of lucked out there. So again, I'll use my highlighter. And so we're looking at 12t squared, and that's going to be plus 16t plus 8t squared plus 4t minus 6 plus 15, or quality 5, t cubed minus 15t. So whatever like terms we can get out of this or what we're going for, and then that should do it, unless there's something extraordinary we can do beyond that. But we'll see. All right, so just going across the line, looking for a power of 3. Got one there. Got one there. I don't see anything else. So 20t cubed. Another highlighter. Let's see, looking for the t squareds. I'm up to 22, 34, 42. I think that's it. Double check that. 22, 34, 42, I think, plus 42t squared. 36t minus 15t, it's 21t. Plus 16 is 37t. 41t, back to 26t. All right. Just double checking those. I think negative 30. Oh wait, is it 22? 21, 37, it should be 22. Because the two 15s give me a negative 30, add to 36 gives me a 6, plus the 16 gives me a 22. And then the last one, I guess I don't need to highlight them because they're the only things left. We have negative 18 plus 8 is negative 10, minus 6 is going to be a negative 16. All right, so barring anything too crazy here in terms of computational error, this looks like it could be it. But I also see here that we have some common factors. I mean, so it might be worth looking into, but we don't want to spend too much time getting bogged down with the algebra of it. What we can do is let any of our calculators, whatever calculator you like using, give us a look at the polynomial, just so you don't have to get into like rational root theorem and things like that. Even though that's kind of a pain, especially if you hear the terms rational root or the term rational root theorem, and you're like, "What the hell is that?" If that's the case, then it wouldn't be helpful at all anyway. Let's see. It doesn't look like a clean intersection. Maybe it is. It looks like it could be. Well, we'll just grab it. 0.388. All right. So I'm not too excited about trying to figure out any meaningful factors of this, except to say that there does appear to be a scalar that can be factored out, but without any context, it doesn't seem to be overly pressing to do that sort of thing. All right, so this would be the derivative of those two components. All right. So then next up would be the cross products derivative. And if you look at the relationship, the cross products derivative has the same look and feel as the dot products derivative. So, you know, we're kind of looking at the same, you know, idea roughly. But what I can do, and I'll show you. I mean, there's the long way and there's the short way. I can bring you in warm or I can bring you in cold. You know, it's just one of those ideas. So what I'll do is I'll take you through the, you know, the very procedural way, and then when shortcuts arise, I'll talk about those. But we have our U prime and our U. I'll keep the highlighting on it, I guess. I rewrote it here. So I'm just going to snag that so I don't have to rewrite everything. Got a little extra. Oh, that's wonderful. All right, so, oh, you know what? Now that I think about it, let me get rid of this. That's not as nice as the vector form of U prime. So let me do that. I really want to stick with the theme of being lazy. This serves more of a purpose. Just going to kind of line it up a little bit better. All right, so we got our, this would be U, and this one would be U prime. All right, so U and U prime, you got to find the, well, as it'll turn out, you may or may not need to actually find the cross product, but we'll get into that. Well, I'll show you in a second. All right, so getting into the actual setup is what becomes most important here, because this is the cross product of U and its own derivative. So it's still the derivative of the first times the second. All right, so U prime of t crossed against U prime of t plus the second, I'm sorry, the derivative of the second. Again, just looking at the notation here. The derivative of this, I'm used to my Calc 1 classes where I would say first times derivative of the second plus the second times the derivative of the first. But here we kind of want to stick with the prescribed approach of the derivative of the first part times the second part plus the second part times the derivative of the first part. All right, so I took care of the derivative of the first part times the second part. Now I'm pulling the first part as is, U of t, crossed against the derivative of the second part. The derivative of a derivative would be the second derivative. All right, so it's easy to get your wires crossed. I just showed you what that looks like. So you just got to be really careful. But I pulled down all the information that we had from the, oh, I didn't want to do that, resize. Pulled down all the information I had from the previous work that we did. Some of it will be more useful than others. All right, so really sucking battery here. So let's take a look back. Just, I'm going to call a timeout real quick and bring you back here somewhere, wherever I put it. Back in our talk about cross products, way back in time. And it's a property that we didn't really touch on, but it was there. Oh, why? There we go. the cross product of a vector and itself. Right? The cross product of a vector and itself gives the zero vector. Because if you really think about it, a cross product is a vector that's perpendicular to two other vectors, so orthogonal to the other two vectors, or the two vectors that make up that cross product. So if I'm looking at this and saying, okay, well, I get two vectors that are identical to one another, what's my only possibility? Well, I can't go up, can't go down, can't go left, can't go right. The only place that I could go is just kind of stay where I'm at the origin, right? So it's kind of like saying uncle and saying, you know, forget it, there's nothing here, right? But if you want to look at it in a more geometric sense, we know that the magnitude of the cross product gives us the area of the parallelogram that is created by the two vectors, right? If we're in 2 dimensions, if we're in 3 dimensions, parallelepiped, right? If that's the case, then the only way that we're going to contain zero area would be if the two vectors are the same. The only way that we would contain zero volume, well, actually, there's a couple of ways. If they're all coplanar, but also if all 3 vectors in 3 dimensions are exactly the same. Long story short, too late. That's your little time saver. If I can get back to the page efficiently, eventually. That tells us that this piece right here, which is a cross product of 2 vectors that are identical, is going to go to 0. AKA, it's irrelevant, right? So that's leaving me with the idea that, okay, well, then I really just, in order to find the derivative of a cross product of a vector and its derivative, all I really need to do is cross the original vector valued function with its second derivative. Right? So I take some time here to muscle out the second derivative, which really doesn't take much muscling, to 0, 6t. Right? And so it turns out that I didn't really need this vector except to help me find the second derivative. If I can get my highlighter to work. Well, I'm really just dragging the highlighter. All right, so these are the two that I'm pairing up. All right. So I'm going to find the cross product ijk. Move that k over a smidge. T cubed minus, squared, sorry, minus 3, 2t plus 4, t cubed minus 3t, 2, 0, 6t. Now you still got a little bit of work ahead of you, but I think anybody here would sign up for computing one cross product as opposed to computing 2 of them. Right? So that's really what the benefit is there. Right? So I'm going to have something I, and you know what, we could kind of do it on the fly. I don't want to waste too much time. Right? If we're focusing on the I part of it, and that 0 helps a lot. I'll use highlighter though. So here's the I information. This is the stuff we care about for I. You know, ignoring the column headings. Diagonal down minus diagonal up. So 6t multiplied by 2t plus 4 minus diagonal up is just going to be 0. So that's my I component. Minus, now I want my j component. So everything except for the j stuff. Diagonal down minus diagonal up is going to be a little bit more involved, for lack of a better term. So we're looking at 6t times 2t minus 2. I said 2t. I meant to say t squared. I was writing t squared and I erased it because I thought I actually wrote what I said. Oh, yeah, yeah. Minus, poor quality, minus 2 times t cubed minus 3t. All right, I'm going to resize. All right, so that's my J stuff. I got to get the J in there, I suppose. Close the overall parentheses. I'll make them stand out a little bit more. Hmm. And then the K part of it, so the columns that don't involve a K, diagonal down, irrelevant, gives me a 0, minus diagonal up, that's going to be minus, poor quality, minus 2 paren 2t plus 4 K. And then, you know, the housekeeping part comes into play. Resize. Doesn't make it look any nicer. And, you know, the housekeeping is really just with the hope that maybe we'll get something that looks a little simpler. But, you know, for the first and last terms of it, you know, like we're really not going to get anything simpler. So you can leave those as is. 6t. Actually, we can even go the other way and pull out a 2. So 12t, t plus 2, I, minus. Now, for this, you might want to just kind of save yourself the time and just kind of, let me get a different highlighter color here. Chuck this stuff off on the side here. Just go beep. So that's going to be 12t cubed minus 18t minus 2t cubed plus 6t. All right, so that combines to give me 10t cubed minus 12t. So that actually, I mean, that'll clean up a smidge. Nothing too crazy, but it is something. So I can pull out a 2t, so minus 2t. So that's 5t squared minus 6. That's my J component. The only way that's going to factor further is if you get radicals involved. There might be a time or place for that, but this isn't it. Right, so I pull out a t, I'm sorry, 2 here. So minus 4t plus 2k. All right. Now, without knowing what we're doing with this, again, just like everything else, it doesn't really have too much meaning, but the skill of finding the derivative involving the cross product is really what we're working on at this point. Right? At least that was the goal of this question, or these questions. So let me stop that video.